Good morning, teenagers. This is Mr. Williams, and you'll be watching this on Monday, February the 3rd. I'm making this video for AP Physics 1. When I spoke with you last, we did a quick derivation on how to find the center of gravity. And then I gave you a single homework assignment from the night book. Your homework assignment was page 221, number 27. And I feel pretty good about giving you this assignment because this assignment straight up just reviews whether or not you understood the question, the derivation that I did. So let's look at number 27. Here it is in your book. You should have worked on this over the weekend, and it should not have taken you very long. It says a 1.7 meter long barbell has a 20 kilogram weight on its right end and a 35 kilogram weight on its left end. If you ignore the weight of the bar itself, how far from the left end of the barbell is the center of gravity? So we're ignoring the weight of the bar. Where is the center of gravity if the 8 kilogram mass of the barbell itself is taken into account? Right. Part B is much harder than Part A. And I'm going to do this, but before I do it, I'm going to repeat my derivation, just so that if anybody was absent, and there were some people absent, that you can see it, and also never hurts to review. Okay, let's imagine a barbell kind of thing. And it has a pivot at the center of gravity. That means, okay, first of all, I need to set my origin some arbitrary distance over here. I don't know where my origin will be, but let's just put it arbitrarily over here. We will call my origin x sub 0. Then, let me look back at the diagram so you guys can see it. This diagram is found on page 204. It's figure 7.29. So we will call this x sub 1, and then, so the distance, this distance here from x sub 0 to x sub 1, this distance is x sub 1, and the distance from x sub 0 to here, we're going to call x sub cm, which is the distance to the center of mass, cm, center of mass. And then we'll call this x sub 2, because that's the distance to the second object that's being pivoted. So the distance from my arbitrary origin, which is, I have put somewhere to the left here, distance from my origin to the far left-hand side of the barbell is x sub 1. The distance from my origin to the center of mass is x sub cm. And the distance from my origin to the far right-hand part of my pivoting object is x sub 2. As far as the object is concerned, they don't care about this object doesn't care about where I put my origin in the slightest. This object cares about how far the left-hand side is from the origin. How far the left-hand side is from the pivot, and how far the right-hand side is from the pivot. So this is going to be the radius. This is going to be a radius 1. Because remember, when you're calculating torque, it's the distance from the r is going to be the length of the radial line, and the radial line is going to go from the axis of rotation out to where the force is applied. And the gravitational force is applied straight down. Before it starts to pivot, it's applied straight down here at a 90-degree angle. This is the radial axis. This is the radial line. The length of the radial line is R1. And it goes from the center of the mass to the pivot. On the other side, we'll have another radial line length. That'll be R2. So this is the radial axis. This is the radial line here. This is the object, and the force is being applied here. So we have our 90, 90, 90. Okay. If the object is completely balanced, so that it is not moving up or down, it's not teeter-tottering or seesawing in any way, then that means that the torques are balanced. So if you think about the torque on this side, the force of gravity is pulling down on this object. If I could make this disappear, how would this pivot? Would it pivot clockwise? Would it pivot counterclockwise? Or would it not pivot at all? If you think about it, it's pretty obvious. It would pivot counterclockwise, and in physics and math, counterclockwise is positive. So this would be a positive torque. We'll call this torque 1. Now let's reverse it. On this side, if I could make all this disappear, so this disappeared, would this radial arm and the object attached to it, would it pivot in a clockwise direction, in a counterclockwise direction, or would it not pivot at all and just hang out there? That's pretty obvious as well, that it would pivot like this, and this is a clockwise direction. Clockwise is negative in physics and mathematics. So this would be a negative torque 2. I just said verbally a couple minutes ago that the torques have to be balanced. Therefore, the sum of all torques that are present must be equal to 0. So 0 is going to be equal to the sum of my torques, and the torques present are torque 1 and torque 2. So torque 1 plus a negative torque 2. Torque is defined as R times F times sine of phi. In this case, phi is 90 degrees here, and it's negative 90 degrees here. And I already took care of the negative verbally and wrote it in. So I don't need to worry about phi. I can just call it R times F. This is going to be R1 F1 plus a negative R2 F2. This is kind of awkward. I can just, instead of saying plus and negative, I'm just going to say minus from now on. Now, R doesn't appear in relation to my origin, so we're going to have to deal with that. And F, what is the force that's being exerted here? It's going to be force. It's going to be the force of weight, so this is going to be mg. So 0 is going to be equal to, what is R1? R1 is this distance minus this distance. So it's x sub cm minus x sub 1. It's the difference between these two. So if I go from here to here, that's x sub cm. And if I go from here to here, it's x sub 1. So x sub cm, this distance, minus this distance. So this distance minus this distance gives me that distance, which is R1. And then that is minus R2 is going to be this distance minus this distance, which gives me that. So it's going to be x2 minus x sub cm times mg, m2g. Yeah, my 2 looks awkwardly placed there, but sometimes I'm an awkward person, so there we go. I have g in both terms. If I divide everything by g, g will disappear, so I'm going to cross g out. I'm going to distribute the m's inside. So 0 is going to be m1 x sub cm minus m2 x sub 1. So the m gets distributed in and then the negative. So minus m2 x sub 2. The m gets distributed in, and then the negative. So this is going to become positive. Plus m2 x sub cm. I am trying to find the distance from my origin to the center of mass. So I'm going to be solving for x sub cm. So this and this, these two terms, I don't need on this side. I'm going to shift them to the other. So I'm going to add this to both sides. I'm going to add this to both sides. I'm going to spread out. Actually, let's not spread out. Let's just keep doing it here. So this is going to be m2 x sub 1 plus m2 x sub 2 is equal to, now I have this and this left on this side, m1 x sub cm plus m2 x sub cm. Since I have x sub cm in both terms, I can pull it out. So this becomes x sub cm multiplied by m1 plus m2. I can divide both this side and this side by m1 plus m2. I'll get x sub cm is equal to m2x1 plus m2x2 divided by this chunk that I divided on both sides, m1 plus m2. That is the derivation for how to find the center of mass. In words, this means the distance to the center of mass of a pivoting object is equal to the mass on the right-hand side multiplied by the distance from the origin to the left-hand side plus the mass on the right-hand side multiplied by the distance from the origin to the right-hand side divided by the mass on the left-hand side plus the mass on the right-hand side. I think it would be entirely foolish of you to memorize this. This will not appear on your AP exam, but you will need to be able to do this derivation. There have been some questions in the past that required you to be able to do this derivation. So you need to be able to draw this picture on your own and do this derivation on your own. Now, let's move on to problem number 27. It says that there is a 1.7 meter long barbell. It next says it has a 20 kilogram weight on its right end. And a 35 kilogram weight on its left end. So this will be M2, and this will be M1. Part A says, if you ignore the weight of the bar itself, how far from the left end of the bar, so left end's over here, how far from the left end of the bar is the center of gravity? Okay. Going back up to our example, we can set this origin anywhere we want. And I would suggest the easiest place for us to put it is right on x1. So if we put the origin on x1, then this equation would make x1 become 0. You guys understand what I'm saying? Look, we can set the origin to be anywhere we want. It could be a million miles that way, or it could actually be over here, which would kind of maybe mess with their signs a little bit. But we can move this origin all the way up to here. If we did that, x1 becomes 0 because the distance between x of 0 and x of 1, there isn't any distance. They're on top of each other, so it's 0. x1 would be 0. And everything else would be the same. I'm going to do that because it makes my equation easier. It would make this equation, this term would go away. So part A, I would say x sub cm is going to be equal to, the equation that we derived is this. But if I set the origin at x1, which I can do because it's arbitrary and my choice, then it becomes so then mass 2 is 20. And the distance from the origin to mass 2 is 1.7 meters. And the two masses added together is 20 plus 35. So I'm going to plug it into my calculator. You guys, I don't know where my blue light blue calculator went. If you don't mind checking your backpacks at home to see if maybe somebody picked it up. Okay, 20 times 1.7 divided by 20 plus 35. That's 0.61 meters. So I have, here's from the book, this is what they say the answer is. So this is the answer key they give teachers. And they round a little, so I have 0.618, and they rounded it to 0.62. So good, I got the answer right there. The trick was just to move the origin over here because I can arbitrarily decide where the origin is. Okay, let's go on to part B. Let's see if I can do that. If you ignore, no, that's part A. Where is the center of gravity if the 8 kilogram mass of the barbell is taken into account? So the barbell has an 8 kilogram mass. So it's the same kind of deal as before. So we have a barbell on this end and another barbell on this end, and this one is, and the distance is still going to be the same. It's kind of off kilter, but whatever. But the difference is now I have to take into account that the barbell itself has a mass. So this is M3. So I'm for M3 is equal to 8 kilograms. Okay. And Lord only knows where my pivot is. So if my pivot is somewhere, I've got to find where it is. I'm going to x sub cm somewhere. Okay. I think we're going to actually have to rederive the equation. Yep, we're going to have to rederive the equation. So this is what, yeah, I remember this from last year. Okay, so this is why I have to, this is why we need to know how to derive the equation. You can't answer part B without coming up with a new equation. This equation here is not going to work because now we have 3 pivoting objects. In the example from the book, we only have 2 pivoting objects. We assume that this is massless, the pivot bar. Yeah, but here, you know, that was the assumption in the book. But now we have 3 objects that are pivoting. We have the mass on the left, we have the mass on the right, and we also have the bar, which is a pivoting mass. So, bum, bum, bum. So let me redo my derivation. So let's say that I set an arbitrary origin, x sub 0 here. And here's my left barbell. So that's going to be x sub 1. And then we're going to have a bar and it will have a, what do you call it? It will have a distance to the center of its mass. So I guess we'll call that x2. So the center, it should be right in the center of the bar. If the bar is of uniform density, that's going to be right in the center of the bar. So this would be x sub 2. And then the pivot, let's see, it's more massive on this side, so I assume that the pivot would be somewhere over here. So x sub cm would be like over here. And then we'll have this over here, which is going to be x sub 3. So let me just make sure that we're clear on words. If the bar is of uniform density, I would expect that its center of mass would be right in the middle, because you'd have half as much mass on one side and half as much mass on the other. So that would be this line. This is a perfectly spherical barbell, so right in the center of it would be where its center of mass is, and gravity would be pulling right there at the center of mass. And over here, same deal. The center of mass for the entire 3 objects, well, for the barbell, the center of mass is right in the center, but this one has more mass than this one does, so I would expect it would shift the center of mass over towards the more massive one. Just like the example I did in class where I held the ruler like this and I attached the weight on the end. The more weight that I applied, the closer I had to move my finger over towards the weight. So you expect the center of mass to shift towards the more massive object. That was the example I did in class the other day. Okay, let's redo my derivation now. I know that the sum of all torques must be 0 if it's balanced. But I have 3 torques. I'm going to have torque 1. Okay, so let me do my radii first. So the distance from the center of mass, this will be radius 1. And this would be radius 2. And then this is radius 3. So it'd be 3 radii there. And so I'm going to have 3 torques. I'm going to have a torque associated with this radius. So if I dropped everything else off on this side, what would happen? Well, it would torque this way. And that would be a positive torque because it's going counterclockwise. So torque 1 is going to be, well, I'm not going to say equals. I'm just going to say it's positive. And then if my center mass is here and all of this disappeared, then I would expect that the bar, since the pivot would be here at the center of mass for the system, since the pivot would be here, the bar would start to fall this way because it's not at the center of its mass. It's that way. So then torque 2 would be negative, torque 2. And also for radius 3, I would expect it would fall this way. So negative torque 3. Now I don't have to worry about signs of phi. So 0 is going to be equal to a positive torque 1 minus torque 2 minus torque 3. This is a really interesting question. This is definitely the type of question that could be a free response question on your AP exam. So 0 is going to be equal to positive. Now this torque is going to be R times F. So R1 F1 minus R2 F2 minus R3 F3. F in all cases is going to be equal to mg. So it's going to be equal to R1 mg, m1g minus R2M2G minus R3M3G. And the G's can cancel because you can divide G all the way through your equation. And 0 divided by G is 0. And now we have to break out what R1 is. R1 is going to be x sub Cm minus x1. X sub Cm minus x1 times R1 times M1 minus, now R2 is x2 minus x sub Cm. And that is multiplied by M2. And finally, R3 is going to be x3 minus x sub Cm. Holy moly. Okay, let's do what we can here. Let's distribute the m's inside. M1 x sub Cm minus M1 x sub 1 minus M2 x2. Now this minus gets distributed in, so it becomes plus. So the minus and then the M2 plus M2 x sub Cm minus x. Oh, I'm doing the m's first. Minus M3 x sub 3. Now the minus gets distributed and the m gets distributed, so plus M3 x sub Cm. All right, let's take the stuff that doesn't have x sub Cm in it. That's this and this and this. And that junk goes to the other side. So that luckily they're all negative, so I can just add them and they become positive on the other side. So this becomes, oh, hopefully I didn't shift the paper too much. This is what it looks like. These three go to the other side and become positive. So M1x1 plus M2x2 plus M3x3 is equal to, now let's see what's left on this side. Oh, look, all of them have x sub Cm in it. So I'm going to just skip a step. I can pull an x sub Cm out of these three and leave behind M1 plus M2 plus M3. So x sub Cm times M1 plus M2 plus M3. Oh, I can see it, yay. I divide both sides by this nasty junk here. So this nasty bit, divide both sides by it, and I get x of Cm. Writing letters is hard. X of Cm is equal to M1 x1 plus M2 x2 plus M3 x3 divided by M1 plus M2 plus M3. Oh man, I feel so accomplished. This is wonderful. Now let's go back up to what I had. So here's my picture up here. And here's my equation down here. I wish that my my little ladybug weren't so annoying. It can't get the whole picture. It can't get the whole paper in one fell swoop. So I need to look and see if I can either make this easier or if this is just the way it is. So M1, I know what that is. X1. Why don't I do the same trick that I did before and take the origin and shift it all the way over to x1, because that'll make it easy. So if I shift the origin over to x1, then x1 becomes 0. So this, I like that. I like to make things 0. But x1 doesn't appear anywhere else. So then M2, x2. So M2 is this. X2 would then just be 1.7. Yeah, so I'm good with that. Oh, wait a second. No. If I shifted the origin to x1, then x2 should be right in the middle of my barbell. So x2 should be half of 1.7. x2 should be 1.7 meters divided by 2. All right. So that should be 0.85. Because the bar, its center of mass should be half, it should be right in the middle of the bar. So now I know what x2 is, so I'm okay with that. And x3 is going to be the whole distance. x3, if I put the origin here, x3 is going to be the length of the bar. So x3 is going to be equal to 1.7 meters. Right? As long as I set the origin with origin on x1. So if I put the origin on x1, then x2 is halfway in the middle of the bar, and x3 is the whole bar. So now I know what x2 and x3 are, and x1 becomes 0, and I know the masses. Yay! I can do this. So the distance to the center of the mass, I can't make those m's for some reason. So the distance to the center of mass is going to be m2, which is 20 kilograms, times x2, which is 0.85 meters, plus m3, which is 20 kilograms. Oh, I totally screwed up. I should have called this M2. Because, see, I called this torque 2, I called this radius 2, so I should have called the bar M2. And this, it wasn't a big mistake, but I should have called this M3. And I've been referring to it as M3 throughout. So, I'm sorry about that. This should have been M1, M2 is the bar, and M3 is this. That's okay. That just means that this is actually not 20. It's actually 8. So 8 kilograms times 0.85 plus 20 kilograms times what is distance 3 is 1.7 divided by, and then I have to add my masses together, 35 plus 8 plus 20. So put a parentheses around my numerator, 8 times 0.85 plus 20 times 1.7, close parentheses, divided by, open parentheses, 35 plus 8 plus 20, close parentheses, and I got 0.647 meters. And let's take a look at the answer key here. So the answer key says 0.65. So yes, that's exactly right. If you round, it's 0.65. So I got the correct answer. I made a really minor error up here when I first started out. I called this M3 and that M2, but this is really M2 because I referred to, in this drawing, I referred to the bar with radius 2 and torque 2. And I referred to the right-hand side with radius 3 and torque 3. So this should have been mass 3 and that should have been mass 2. Other than that, everything was right. Okay, that was exciting and fun. I really enjoyed that. I hope that you had a good time with that too. That was a good puzzle. I really like that problem. Let's give you a couple other homework problems. So let's do homework page 221. Number 28. Let's give you one problem. Work on it. It should take you somewhere between 15 and 30 minutes. All right, folks. Have a great evening. Bye-bye.